Imagine a 20-mile bridge stretching across deep, storm-lashed ocean waters supporting thousands of vehicles every hour. Now imagine the earth beneath it rupturing violently. A magnitude 9 earthquake strikes without warning. What happens next? Do the towers snap? Do the foundations fail? Or does the bridge survive? Welcome to Civil Engineering Edge, where today we dive into one of the most terrifying challenges in modern infrastructure protecting colossal sea bridges from seismic annihilation. We're uncovering the groundbreaking seismic isolation systems, energy-dissipating technologies, and revolutionary foundation designs that allow these giants to defy the planet's most violent shudders. Stay with us because what keeps these titans standing will truly amaze you. Welcome again to Civil Engineering Edge, your trusted destination where engineering theory meets real-world megastructures. This channel is built for civil engineering students sharpening their fundamentals, professionals seeking advanced insights, and developers eager to understand the science behind resilient infrastructure. In today's rapidly changing world, infrastructure is no longer judged solely by strength, it is judged by resilience. As coastal cities expand and global trade intensifies, mega sea bridges have become lifelines connecting economies, cultures, and continents. But these marvels of engineering face an invisible enemy, earthquakes beneath the ocean floor. In this video, we'll break down how engineers are redefining seismic design, combining advanced materials, innovative isolation systems, and high-fidelity computational modeling to ensure these structures remain operational even after extreme seismic events. This is not just engineering, it's engineering at the edge of possibility. Colossal visions. Engineering sea bridges for a shifting Earth. Mega sea bridges represent the pinnacle of human ambition in civil engineering. Unlike conventional bridges, these structures are built in deep water, exposed to waves, currents, typhoons, corrosion, and most critically seismic forces originating beneath unstable seabeds. What makes these bridges extraordinary is not just their length or height, but the complex interaction of forces acting on them simultaneously. During an earthquake, a sea bridge doesn't just shake, it moves differently at every support, while water, soil, and structure respond together as a coupled system. This dynamic behavior demands a completely new design philosophy. Modern engineers no longer design these bridges to be rigid. Instead, they are engineered to move intelligently to absorb, redirect, and dissipate seismic energy without catastrophic failure. Flexible pylons, seismic bearings, dampers, and foundations capable of controlled deformation are now central to design. Mega sea bridges are no longer static monuments of concrete and steel. They are living structural systems engineered to adapt to a shifting Earth. Every design decision from tower geometry to pile embedment depth is guided by performance-based seismic design, ensuring survival under worst-case earthquake scenarios. The impossible scale. Why mega sea bridges in seismic zones are humanity's ultimate engineering challenge. Building a mega sea bridge in a seismic zone is often described as engineering against nature itself. The scale alone is overwhelming: kilometers of span length, towers taller than skyscrapers, foundations embedded deep into the ocean floor. Now add earthquakes to the equation, and the challenge multiplies exponentially. Unlike land-based structures, sea bridges are founded on soft marine sediments, which amplify seismic waves and increase ground motion. Phenomena such as liquefaction, lateral spreading, and seabed fault rupture can occur simultaneously, threatening the stability of foundations. Traditional design assumptions simply do not apply. Additionally, seismic waves do not arrive uniformly. One pier may experience peak acceleration seconds before another, creating asynchronous loading that twists and stretches the structure. Expansion joints, bearings, and cables must accommodate massive displacements without losing load-carrying capacity. Construction itself is a challenge, installing piles hundreds of meters long with millimeter-level precision in moving water, all while accounting for future seismic demands. This is why mega sea bridges in seismic zones are considered the ultimate test of civil engineering expertise. They demand interdisciplinary mastery: structural engineering, geotechnics, materials science, ocean engineering, and advanced computation working together in perfect harmony. Bridging continents, defying quakes, iconic mega bridges pushing the limits to 100+ words. Some of the world's most ambitious sea bridges are already proving that seismic resilience is achievable. Take the Hong Kong-Zhuhai-Macau Bridge, a 55-kilometer megalink constructed in one of the world's most seismically active and typhoon-prone regions. Designed to withstand magnitude 8 earthquakes, it incorporates seismic isolation bearings, massive steel concrete composite towers, and deep pile foundations socketed into bedrock. Japan offers even more striking examples. Located on the Pacific Ring of Fire, Japanese sea bridges are engineered with a fail-safe philosophy. Structures like the Akashi Keikyo Bridge use tuned mass dampers, flexible steel towers, and advanced seismic sensors that allow controlled movement during earthquakes, preventing collapse while preserving structural integrity. What unites these bridges is not brute strength, but intelligent flexibility. They are designed to deform without breaking, dissipating seismic energy through bearings, dampers, and sacrificial elements. These projects demonstrate that with the right technology and design philosophy, engineers can bridge continents while defying earthquakes, setting new global benchmarks for resilient infrastructure. The invisible threat: seismic risks anchored in volatile ocean floors. The most dangerous enemy of mega sea bridges is not visible, it lies beneath the ocean floor. Marine seismic conditions are uniquely complex. Earthquake waves travel through layers of water, soft sediments, fractured rock, and fault zones before reaching the structure. These layers distort, amplify, and prolong ground motion, subjecting foundations to extreme cyclic loads. One of the greatest risks is soil liquefaction, where saturated sand temporarily behaves like a liquid during shaking. This can cause piles to lose lateral support, leading to excessive displacement or even collapse. Fault rupture beneath foundations poses another severe threat, capable of offsetting piles and piers by meters. Engineers combat these invisible dangers using deep-seated foundations, ground improvement techniques, seismic isolation at the foundation level, and real-time monitoring systems. Advanced numerical modeling such as nonlinear time history analysis and soil structure fluid interaction simulations allows engineers to predict how bridges will behave during extreme events before construction even begins. Understanding and controlling these hidden seismic risks is what transforms mega sea bridges from vulnerable giants into resilient lifelines capable of standing strong when the Earth itself turns hostile. The impossible scale. Why mega sea bridges in seismic zones are humanity's ultimate engineering challenge. Building a mega sea bridge in a seismic zone is often described as engineering against nature itself. The scale alone is overwhelming: kilometers of span length, towers taller than skyscrapers, foundations embedded deep into the ocean floor. Now add earthquakes to the equation, and the challenge multiplies exponentially. Unlike land-based structures, sea bridges are founded on soft marine sediments, which amplify seismic waves and increase ground motion. Phenomena such as liquefaction, lateral spreading, and seabed fault rupture can occur simultaneously, threatening the stability of foundations. Traditional design assumptions simply do not apply. Additionally, seismic waves do not arrive uniformly. One pier may experience peak acceleration seconds before another, creating asynchronous loading that twists and stretches the structure. Expansion joints, bearings, and cables must accommodate massive displacements without losing load-carrying capacity. Construction itself is a challenge, installing piles hundreds of meters long with millimeter-level precision in moving water, all while accounting for future seismic demands. This is why mega sea bridges in seismic zones are considered the ultimate test of civil engineering expertise. They demand interdisciplinary mastery: structural engineering, geotechnics, materials science, ocean engineering, and advanced computation working together in perfect harmony. Bridging continents, defying quakes, iconic mega bridges pushing the limits to 100+ words. Some of the world's most ambitious sea bridges are already proving that seismic resilience is achievable. Take the Hong Kong-Zhuhai-Macau Bridge, a 55-kilometer megalink constructed in one of the world's most seismically active and typhoon-prone regions. Designed to withstand magnitude 8 earthquakes, it incorporates seismic isolation bearings, massive steel concrete composite towers, and deep pile foundations socketed into bedrock. Japan offers even more striking examples. Located on the Pacific Ring of Fire, Japanese sea bridges are engineered with a fail-safe philosophy. Structures like the Akashi Keikyo Bridge use tuned mass dampers, flexible steel towers, and advanced seismic sensors that allow controlled movement during earthquakes, preventing collapse while preserving structural integrity. What unites these bridges is not brute strength, but intelligent flexibility. They are designed to deform without breaking, dissipating seismic energy through bearings, dampers, and sacrificial elements. These projects demonstrate that with the right technology and design philosophy, engineers can bridge continents while defying earthquakes, setting new global benchmarks for resilient infrastructure. The invisible threat: seismic risks anchored in volatile ocean floors. The most dangerous enemy of mega sea bridges is not visible, it lies beneath the ocean floor. Marine seismic conditions are uniquely complex. Earthquake waves travel through layers of water, soft sediments, fractured rock, and fault zones before reaching the structure. These layers distort, amplify, and prolong ground motion, subjecting foundations to extreme cyclic loads. One of the greatest risks is soil liquefaction, where saturated sand temporarily behaves like a liquid during shaking. This can cause piles to lose lateral support, leading to excessive displacement or even collapse. Fault rupture beneath foundations poses another severe threat, capable of offsetting piles and piers by meters. Engineers combat these invisible dangers using deep-seated foundations, ground improvement techniques, seismic isolation at the foundation level, and real-time monitoring systems. Advanced numerical modeling such as nonlinear time history analysis and soil structure fluid interaction simulations allows engineers to predict how bridges will behave during extreme events before construction even begins. Understanding and controlling these hidden seismic risks is what transforms mega sea bridges from vulnerable giants into resilient lifelines, capable of standing strong when the Earth itself turns hostile. Dancing with tremors, the art of seismic isolation. When earthquakes strike, traditional thinking suggests resisting motion with brute strength. But modern seismic engineering follows a radically different philosophy: let the structure move, but control how it moves. This idea lies at the heart of seismic isolation, a design strategy that allows mega sea bridges to dance with seismic forces rather than fight them. Seismic isolation works by decoupling the superstructure from destructive ground motion. Instead of transmitting earthquake energy directly from the foundation into the towers and deck, isolation systems act as a buffer layer. They filter and reshape seismic waves, dramatically reducing acceleration, internal forces, and structural damage. For mega sea bridges, isolation is especially critical. Earthquake motions beneath the seabed are often amplified by soft marine soils and arrive asynchronously at different piers. Isolation systems allow each support to respond independently while preserving global stability. The result is a structure that moves smoothly, slowly, and predictably even during violent ground shaking. Rather than sharp, brittle failure, isolated bridges exhibit large but controlled displacements, protecting key structural elements like pylons, cables, and deck connections. This approach not only prevents collapse, but also ensures post-earthquake serviceability, which is vital for emergency response and economic continuity. Seismic isolation is no longer an optional enhancement, it is an essential design philosophy for next-generation sea bridges in earthquake-prone regions. Uncoupling the beast, how base isolation bearings let bridges float. At the core of seismic isolation are base isolation bearings, engineered devices placed between the bridge superstructure and its foundations. Their job is simple in concept, but revolutionary in impact. Uncouple the bridge from ground motion. One of the most widely used systems is the lead rubber bearing LRB. These bearings consist of alternating layers of rubber and steel with a solid lead core at the center. During an earthquake, the rubber layers provide flexibility, allowing horizontal movement, while the lead core yields plastically, dissipating seismic energy as heat. This combination reduces transmitted acceleration while providing restoring force to recenter the bridge after shaking stops. Another advanced system is the friction pendulum bearing FPB. These bearings allow the bridge deck to slide along a curved, concave surface during seismic motion. The brilliance of this system lies in physics. The sliding motion increases the natural period of the structure, moving it away from the dominant earthquake frequencies. Gravity then acts as a natural restoring force, pulling the bridge back to its original position. In mega sea bridges, these bearings can allow displacements of hundreds of millimeters without structural damage. To an observer, it appears as if the bridge is calmly floating, while the ground beneath it convulses violently. This intentional flexibility transforms earthquakes from catastrophic events into manageable motions, redefining how engineers protect massive structures. Smart damping systems, viscous dampers, and tuned mass dampers explained. While isolation systems reduce how much earthquake energy enters the structure, damping systems control what happens to the energy that does get in. This is where smart damping devices play a critical role. Viscous dampers function much like automotive shock absorbers. Filled with high viscosity fluid, these devices resist motion by converting kinetic energy into heat as fluid is forced through narrow orifices. During an earthquake, viscous dampers generate forces proportional to velocity, making them highly effective in reducing both displacement and acceleration. In mega sea bridges, viscous dampers are often installed between deck segments, towers, or pylons. They are especially effective in controlling long-period motions common in large-span structures. Their performance is stable, predictable, and effective across a wide range of earthquake intensities. Tuned mass dampers (TM-DIS) take a different approach. These systems consist of a large secondary mass, tuned to move out of phase with the bridge's primary vibration mode. When the structure begins to sway, the TM deoscillates in the opposite direction, canceling out motion and reducing amplitude. For sea bridges, TM-DIS are often placed inside towers or beneath decks to control wind and earthquake-induced vibrations. Together, viscous dampers and TM-DIS transform violent seismic energy into controlled, dissipated motion, protecting structural integrity and extending service life. Real-world application: visualizing seismic isolation through animated simulations. Understanding seismic isolation truly clicks when we see it in motion. Modern engineering relies heavily on animated simulations and digital twins to visualize how mega sea bridges behave during earthquakes. In these simulations, seismic waves propagate through the seabed, shaking the foundations violently. Without isolation, the bridge deck mirrors this motion: rapid acceleration, large internal forces, and potential failure points. But when isolation systems are activated, the difference is dramatic. The foundation moves aggressively, yet the deck above glides smoothly. Base isolation bearings slide, flex, and rotate, allowing controlled horizontal displacement. Viscous dampers glow in simulations as energy is absorbed and dissipated. Tuned mass dampers swing rhythmically, counteracting structural motion. Engineers use nonlinear time history analysis to simulate real earthquake records, sometimes thousands of scenarios, ensuring performance even under worst-case conditions. These visual tools are invaluable for design validation, stakeholder communication, and safety approval for students and professionals alike. These simulations reveal a powerful truth. Seismic resilience is not about rigidity, it's about orchestrated motion. Mega sea bridges don't resist earthquakes. They dance with them, moving gracefully through chaos and emerging intact. Groundbreaking foundations, anchoring giants to the deep. For mega sea bridges, the most critical structural elements are the ones no one sees. Hidden beneath waves and sediment, foundations carry the fate of the entire structure. When earthquakes strike, superstructures may sway and isolate, but if foundations fail, collapse is inevitable. Unlike land-based bridges, sea bridges are anchored into complex, layered marine geology, soft clays, loose sands, fractured rock, and active fault zones. Seismic waves passing through these layers amplify motion, generate poor water pressure, and threaten stability. Engineers must therefore design foundations not just for strength, but for survivability under extreme deformation. Modern foundation design embraces redundancy, ductility, and adaptability. Engineers allow controlled rotation, bending, and energy dissipation at the foundation level while preventing brittle failure. This approach transforms foundations from passive supports into active seismic-resisting systems. Advanced geotechnical engineering has made it possible to anchor massive pylons in depths exceeding 100 meters, ensuring stability even under combined loads from earthquakes, waves, currents, and ship impact. These foundations are the silent guardians of mega sea bridges, enduring forces far beyond what the eye can see, beyond bedrock. Deep foundations in challenging marine geology. In many marine environments, reaching competent bedrock is either impractical or impossible. Instead, engineers rely on innovative deep foundation systems capable of performing reliably in weak or highly variable soils. Large diameter drilled shafts, often exceeding 6 to 10 meters in diameter, are among the most effective solutions. These shafts extend deep into the seabed, developing capacity through a combination of end bearing and side friction. During seismic events, their massive stiffness and ductility allow them to resist lateral loads and bending moments while accommodating cyclic deformation. Caisson foundations, both open and pneumatic types, are another cornerstone of mega sea bridge construction. These hollow, box-like structures are sunk into the seabed and filled with reinforced concrete, forming extremely stable bases. Caissons distribute loads over large areas, reducing stress concentration and improving seismic performance. In some projects, hybrid foundation systems are used, combining piles, shafts, and caissons to optimize performance under multi-directional seismic forces. Engineers also employ rock-socketed piles, anchoring foundations into fractured rock layers for enhanced lateral resistance. These deep foundation systems do more than support vertical loads. They are designed to flex, rotate, and dissipate energy, ensuring that even when the earth moves violently, the bridge remains firmly anchored. Liquefaction and scour mitigation, defending foundations during earthquakes. Two of the most destructive threats to sea bridge foundations during earthquakes are soil liquefaction and scour, often occurring simultaneously. Liquefaction happens when saturated, loose soils lose strength under seismic shaking, behaving temporarily like a fluid. This can lead to loss of lateral support, excessive settlement, tilting, or even collapse of bridge piers. To combat this, engineers employ ground improvement techniques such as vibrocompaction, stone columns, deep soil mixing, and jet grouting. These methods densify soil, increase shear strength, and reduce poor water pressure buildup. Scour, the erosion of soil around foundations due to water flow, becomes even more severe during earthquakes when soil structure is disturbed. Engineers counter this by designing armored protection systems, including rock riprap, concrete mattresses, and geotextile filters around piers. Advanced strategies integrate seismic and hydraulic design, ensuring foundations remain stable under combined earthquake shaking and aggressive water movement. In some cases, sacrificial scour layers are designed to erode while preserving structural integrity beneath. By proactively addressing liquefaction and scour, engineers ensure that foundation performance remains predictable even in the chaotic conditions of a major seismic event. Pioneering geotechnical insights, advanced site investigation, and soil modeling. Modern foundation design for mega sea bridges begins long before construction. It starts with unprecedented levels of site investigation and modeling. Engineers deploy offshore boreholes, cone penetration tests, CPT, geophysical surveys, and seismic reflection profiling to map subsurface conditions in extraordinary detail. These investigations reveal soil layering, fault lines, poor water pressures, and dynamic soil properties critical for seismic design. Data from these studies feed into advanced numerical models, including finite element and finite difference simulations. These potential and foundation response under extreme conditions. Probabilistic seismic hazard analysis (PSHA) is used to evaluate multiple earthquake scenarios, ensuring designs are robust against uncertainty. Engineers also develop performance-based geotechnical designs, focusing on acceptable deformation rather than absolute prevention of movement. These pioneering geotechnical insights allow engineers to predict how foundations will behave before the first pile is installed. The result is safer, smarter, and more resilient mega sea bridges anchored not just in concrete and steel, but in deep scientific understanding of the Earth itself. Models capture soil structure fluid interaction, allowing engineers to simulate earthquake loading, liquefaction, materials that endure, the future of bridge components. In the world of mega sea bridges, materials are no longer passive building blocks, they are active defenders against earthquakes, corrosion, fatigue, and time itself. As seismic demands intensify and service life expectations stretch beyond a century, traditional materials alone are no longer sufficient. Modern bridge engineering is witnessing a materials revolution. Engineers are now designing components that can sense damage, heal microcracks, and adapt dynamically under extreme loading. For seismic resilience, this shift is transformative. Materials are engineered not just for strength, but for ductility, energy absorption, and long-term durability in hostile marine environments. Saltwater exposure, temperature variation, cyclic loading, and seismic shock create a uniquely aggressive setting. Advanced materials must resist corrosion while maintaining mechanical performance during earthquakes. The future of mega sea bridges lies in hybrid material systems, combining conventional concrete and steel with intelligent, high-performance alternatives. These next-generation materials allow bridges to withstand repeated seismic events with minimal degradation, significantly reducing life cycle costs and downtime. In seismic design, materials are no longer a limitation, they are a strategic advantage, redefining what is structurally possible. Self-healing concrete and smart alloys, materials that fight back. One of the most promising breakthroughs in bridge engineering is self-healing concrete. Traditional concrete inevitably develops microcracks due to shrinkage, fatigue, and seismic loading. Left untreated, these cracks allow water and chlorides to penetrate, accelerating corrosion and weakening the structure. Self-healing concrete addresses this vulnerability using embedded bacteria, microcapsules, or mineral admixtures. When cracks form and moisture enters, these systems activate, producing calcium carbonate that seals the cracks autonomously. For mega sea bridges, this means reduced permeability, improved durability, and enhanced seismic performance by preventing progressive damage. Alongside concrete innovation, Smart alloys, particularly shaped memory alloys, are revolutionizing seismic design. These metals can undergo large deformations during earthquakes and then return to their original shape once loading is removed. This self-centering behavior is invaluable for bridge piers, connections, and dampers. In seismic events, SMAs absorb energy without permanent deformation, drastically reducing residual displacement. This allows bridges to remain functional immediately after earthquakes, an essential requirement for emergency response routes. Together, self-healing concrete and smart alloys transform bridges into self-preserving systems capable of resisting, recovering, and enduring seismic punishment far beyond conventional materials. Fiber-reinforced polymers for strength without the weight. Fiber-reinforced polymers, or FRPS, are redefining how engineers think about strength, flexibility, and durability. Made from high-strength fibers such as carbon, glass, or aramid embedded in a polymer matrix, FRPS offer exceptional mechanical properties at a fraction of the weight of steel. For seismic applications, lightweight materials are a major advantage. Lower mass means reduced seismic inertia forces, directly decreasing earthquake-induced demands on foundations and piers. At the same time, FRPS provide outstanding tensile strength, fatigue resistance, and corrosion immunity critical in marine environments. FRPS are increasingly used for structural strengthening, seismic retrofitting, and even primary load-bearing components. Wrapping bridge columns with FRP enhances confinement, ductility, and energy dissipation capacity, allowing them to undergo large deformations without failure. In mega sea bridges, FRPS are also used in cable systems, decks, and protective coatings. Their flexibility allows controlled deformation during earthquakes, while their durability ensures long service life with minimal maintenance. By combining strength and flexibility, FRPS enable engineers to design structures that are not only resilient, but also efficient, ushering in a new era of lightweight, high-performance bridge construction. Integrated sensing and structural health monitoring, bridges that think. The future of seismic resilience lies not just in stronger materials, but in smarter structures. Integrated sensing and structural health monitoring (SHM) systems transform mega sea bridges into intelligent assets capable of assessing their own condition in real time. Embedded sensors such as accelerometers, strain gauges, fiber optic sensors, and GPS systems continuously monitor vibrations, displacement, stress, and environmental conditions. During an earthquake, these sensors capture critical performance data, revealing how the bridge actually responds to seismic forces. This real-time feedback allows engineers to immediately assess damage, determine safety, and decide whether the bridge can remain operational. Beyond emergency response, SHM systems enable predictive maintenance, identifying early signs of deterioration long before visible damage occurs. Advanced analytics and AI algorithms process sensor data to detect anomalies, estimate remaining service life, and optimize inspection schedules. For mega sea bridges, this dramatically reduces maintenance costs and enhances safety. By integrating smart materials with sensing technology, bridges evolve from static structures into living systems aware, responsive, and resilient. This intelligence is key to ensuring that next-generation sea bridges not only survive earthquakes, but continue serving society safely for decades to come. The digital battlefield, simulating seismic survival. Before a single pile is driven into the seabed, today's mega sea bridges are already fighting earthquakes in the digital realm. This virtual battlefield is where engineers test ideas, push limits, and uncover weaknesses without risking lives or billions in infrastructure. Earthquakes are chaotic, unpredictable, and brutally complex. No two events are ever the same. To design bridges capable of surviving these forces, engineers rely on advanced computational tools that can simulate seismic behavior with extraordinary precision. The digital battlefield allows thousands of earthquake scenarios to be tested, refined, and optimized long before construction begins. Through high-performance computing, engineers model the interaction between ground motion, water, soil, foundations, and superstructure as a single integrated system. These simulations reveal how energy flows through a bridge, where stresses concentrate, and how isolation systems, dampers, and materials respond under extreme loading. In this digital space, failure is not catastrophic, it is educational. Every simulated collapse leads to stronger, smarter designs. The result is a new generation of mega sea bridges engineered not by guesswork, but by data-driven certainty. Supercomputer simulations, CFD and FEA in earthquake modeling. At the heart of seismic simulation lies the power of supercomputers. Mega sea bridges involve millions of interacting variables, and only high-performance computing can process this complexity within practical timeframes. Finite element analysis (FEA) is the backbone of structural earthquake modeling. Engineers discretize bridges into millions of elements, each governed by material properties, geometry, and nonlinear behavior. Through time history analysis, real earthquake records are applied to the model, revealing stress, strain, displacement, and potential failure modes across the structure. Complementing FEA, computational fluid dynamics (CFD) models the behavior of water during seismic events. Earthquakes can induce hydrodynamic pressures, wave amplification, and fluid structure interaction effects that significantly influence bridge response, especially for submerged foundations and piers. By coupling CFD with FEA, engineers simulate how seismic waves propagate through soil, interact with water, and ultimately impact the bridge. This integrated approach captures effects that traditional design methods simply cannot. These simulations allow engineers to test extreme scenarios, rare but devastating earthquakes, ensuring bridges are not only code compliant but future-proof. Supercomputers turn uncertainty into insight, making the invisible forces of earthquakes visible and manageable. Digital twins and predictive modeling, virtual replicas that learn. A digital twin is more than a 3D model. It is a living, evolving virtual replica of a real bridge. Built using design data, material properties, and sensor feedback, digital twins allow engineers to simulate and predict structural behavior throughout the bridge's entire life cycle. For seismic resilience, digital twins are revolutionary. Engineers can subject the virtual bridge to thousands of earthquake scenarios, varying magnitude, frequency content, fault location, and soil conditions. Each simulation refines the design, identifying vulnerabilities and optimizing performance. Once the bridge is operational, real-time data from structural health monitoring systems continuously updates the digital twin. This allows engineers to compare predicted behavior with actual performance during minor tremors or environmental loading, improving accuracy over time. Predictive modeling enables what-if analysis. What happens if a stronger earthquake occurs? How will aging materials respond? Which components are most at risk? These insights guide maintenance strategies and retrofit planning. Digital twins shift seismic design from a one-time calculation to a continuous process, ensuring mega sea bridges remain resilient, not just on opening day, but for decades to come. The next frontier: AI and machine learning in seismic design. Artificial intelligence and machine learning represent the next seismic revolution in bridge engineering. Traditional simulations, while powerful, are computationally expensive and time-consuming. AI accelerates this process by learning patterns from vast data sets of simulations and real-world earthquake records. Machine learning models can predict structural response such as displacement, stress, or damage probability in seconds rather than hours. This enables rapid design iteration and early-stage optimization that was previously impossible. AI is also transforming performance-based seismic design. By analyzing millions of potential scenarios, algorithms can identify optimal combinations of materials, isolation systems, and foundation layouts that maximize resilience while minimizing cost. In the future, AI-driven systems may automatically propose innovative bridge designs, evaluate seismic safety in real time, and even adapt control systems during earthquakes. Combined with digital twins and sensor data, AI enables self-learning infrastructure. For mega sea bridges, this means faster innovation, greater safety margins, and smarter decision-making, ushering in an era where bridges are not just engineered, but intelligently designed to survive Earth's most violent forces. Mega sea bridges are more than concrete and steel, they are acts of defiance against nature's extremes. From seismic isolation systems that allow graceful movement, to deep foundations anchored in unstable seabeds, to intelligent materials and AI-driven simulations, every component plays a role in seismic survival. What we've explored today is the future of civil engineering, a future where resilience is designed digitally, validated virtually, and perfected through innovation. These bridges stand as symbols of what humanity can achieve when science, technology, and imagination unite. At Civil Engineering Edge, our mission is to bring you to the forefront of this evolution, empowering students, professionals, and developers with knowledge that shapes the world. If you found value in this deep dive, like the video, subscribe to the channel, and share it with fellow engineers. Stay curious, stay innovative, and remember, the future of infrastructure is built by those who understand it first. See you in the next breakthrough.